Right now, as you listen to this, something could be happening somewhere in the universe that would erase everything. Not an explosion, not a collision, not a beam of radiation you could see coming. A boundary expanding outward at the speed of light, where the rules that hold atoms together, the rules that let stars burn, the rules that allow chemistry, biology, thought, everything you have ever known, simply stop working. And the most terrifying part is not what it does. It is that no signal, no warning, no observation of any kind could ever arrive ahead of it. You would not see it. You would not feel it approaching. One moment, the universe is here. The next, it is something else entirely. And this is not science fiction. It is physics. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Look up at the night sky on a clear evening and find a patch of darkness between two stars. That gap, that little sliver of black between 2 points of light, looks like nothing. It looks like absence. Like the universe simply forgot to put something there. And if you think about space in general, that is probably your default picture. Planets here, stars there, galaxies scattered around, and between all of it, emptiness. A void. The blank canvas on which the universe painted its objects. That picture is wrong. Not slightly wrong. Not oversimplified in some minor technical way that only matters to physicists. It is wrong in a way that changes what the universe is, what matter is, and what you are. Because the empty space between those two stars is not empty. It is full. It is doing things right now that determine the mass of every atom in your body, the strength of every force holding those atoms together, and the reason light travels at the speed it does. The vacuum of space, what you think of as nothing, is one of the most physically active and consequential things in the entire universe. And tonight, that is where we need to start. Because the wave described in the title of this episode, the one that could end everything, is not a wave moving through matter. It is something far stranger. It is a change in what empty space itself is doing. And to understand why that is terrifying, you first have to understand what empty space actually is. In everyday language, a vacuum means the absence of stuff. You pump the air out of a chamber and you have a vacuum. No molecules, no particles, nothing bouncing around inside. That is a perfectly good definition for engineering, for chemistry, for anything involving physical objects at human scales. But in fundamental physics, the word vacuum means something very different. It means the lowest energy state of the fields that fill all of space. And that sentence contains a word that changes everything. Fields. In physics, a field is not a meadow. It is a quantity that has a value at every single point in space. Imagine the temperature in a room. Near the heater, it is warmer. Near the window, it is cooler. The temperature varies smoothly from place to place. That is a field. Not a physical object, not a particle. It is a condition, a value that exists everywhere, and it can change from point to point. Now apply that concept to the entire universe. Modern physics tells us that space is filled with fields. Not one field, many fields, layered on top of each other, coexisting everywhere. There is an electromagnetic field. There is a field for each type of quark, a field for the electron, a field for the muon, a field for the tau particle, fields for the neutrinos. fields associated with the strong and weak nuclear forces. And there is the Higgs field. Every point in the universe, every location you could possibly specify, whether it is inside a star, in the gap between galaxies, or in the room you're sitting in right now, has a value for each of these fields. Most of the time, in what we call empty space, most of these fields are sitting at 0. They are calm, undisturbed, at their lowest possible energy. And that calm, undisturbed, lowest energy state is what physicists mean when they say vacuum. The vacuum is not the absence of fields, it is the fields at rest. It is what the fields are doing when nothing is exciting them. And here is the part that sounds strange but is absolutely central to the physics. Particles are not separate things from fields. Particles are what happens when a field gets excited. Think of a guitar string. When the string is still, it is in its ground state, its lowest energy. When you pluck it, it vibrates. That vibration is a localized excitation of the string, a disturbance that carries energy and moves along the string. A particle is the same idea applied to a quantum field. An electron is not a tiny ball sitting in space. An electron is a specific excitation, a vibration of the electron field. A photon is an excitation of the electromagnetic field. A quark is an excitation of one of the quark fields. Every particle you have ever heard of is a ripple in an underlying field that fills all of space. This is not a metaphor. It is the actual mathematical structure of quantum field theory, the most successful theory in the history of physics. Developed over the course of the 20th century, this framework describes the subatomic world with a precision that is almost absurd. The predictions of quantum electrodynamics have been tested against experiment and found to agree to better than 10 parts in a billion. That is like predicting the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. It is the most precisely confirmed description of nature that human beings have ever produced. And it says, unambiguously, that the universe is made of fields, that what we call particles are excitations of those fields, and that what we call empty space is those same fields in their lowest energy state. But there is something crucial about that lowest energy state that separates quantum fields from ordinary objects at rest. When a guitar string stops vibrating, it stops. It is still. It has 0 energy of vibration and 0 motion. But a quantum field cannot do this. A quantum field in its ground state, the state of lowest possible energy, is not still. It is never still. It fluctuates. This is not because something is disturbing it. It is not because energy is being fed into it from an outside source. It is a direct consequence of one of the most fundamental principles in quantum mechanics, the Heisenberg uncertainty principle. The uncertainty principle states that certain pairs of physical properties cannot both be precisely defined at the same time. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. For a quantum field, this means you cannot simultaneously have a field with a precisely defined value and 0 rate of change. If the field were perfectly still, perfectly at rest with a known value everywhere and no fluctuation at all, that would violate the uncertainty principle. The field would have a definite value and a definite rate of change, both at 0, and quantum mechanics does not allow that. So the field fluctuates, even in its ground state, even when nothing is exciting it, even in what we call the vacuum, the field shivers and trembles at the quantum level. These fluctuations are tiny. They are random. They happen everywhere, at every point in space, continuously. And they are real. They are not a theoretical abstraction. They have measurable physical consequences. One of the most striking confirmations of vacuum fluctuations is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948. Casimir realized that if you place two uncharged, perfectly conducting metal plates extremely close together in a vacuum, the fluctuations of the electromagnetic field between the plates are restricted. Only fluctuations that fit neatly between the plates, whose wavelengths match the gap, can exist in that space. Outside the plates, all fluctuations are permitted. This creates a difference in energy density between the inside and outside of the plates, and that difference produces a measurable force that pushes the plates together. The Casimir effect has been measured with high precision. It is real. It produces a genuine physical force, and the force matches the theoretical predictions derived from quantum vacuum fluctuations. Empty space, the space between those plates with all the air pumped out and no particles of any kind present, exerts a force, not because there is anything there in the everyday sense, because the quantum fields that fill that space, even in their ground state, are not truly at rest. They fluctuate, and those fluctuations carry energy. This energy is called zero-point energy. It is the irreducible minimum energy that a quantum field possesses even when nothing is exciting it. Every quantum field has it. The electromagnetic field has it. The electron field has it. The quark fields have it. All of them, in their ground states, carry some non-zero amount of energy simply because quantum mechanics forbids them from having exactly zero. The implications are profound. The vacuum of space is not nothing. It is a physical system with real energy, real fluctuations, and real measurable effects. It has properties, it has a structure, it has an energy density. And like any physical system, the question of whether it is in its true lowest energy state becomes a legitimate scientific question with potentially enormous consequences. The vacuum is not a backdrop on which the drama of physics plays out. It is part of the drama. And if it carries energy, if it has measurable properties, then those properties could in principle change. That possibility is what makes the rest of this story possible. Another confirmation is the Lamb shift. In the late 1940s, physicist Willis Lamb measured the energy levels of hydrogen with extraordinary precision and found that two energy states that theory predicted should be exactly equal were in fact slightly different. The difference was explained by the interaction between the electron and the fluctuating electromagnetic field of the vacuum. The electron, even in empty space, is surrounded by the ceaseless quantum shimmer of the vacuum, and that shimmer nudges its energy levels by a tiny amount. The Lamb shift was one of the earliest demonstrations that the quantum vacuum is physically real, and that treating empty space as truly empty produces the wrong answers. So when we say the vacuum is the lowest energy state of the quantum fields, we mean the lowest energy state of a system that is never truly quiet. A system that fluctuates inherently. A system that carries energy, exerts forces, and shifts the properties of the matter embedded in it. That is what empty space actually is. Not absence. Activity. The quietest possible version of a system that is always, at some level, alive. Now, most of these fields behave in a way that is relatively intuitive. When nothing is disturbing them, they sit at a value of zero. The electromagnetic field in empty space, far from any charges or currents, has a value of zero. That makes sense. No charges, no field, no excitation, no photon. The field is off, waiting to be turned on by something. The electron field in empty space has a value of 0. No electrons present, no excitation. Same for the quark fields, the neutrino fields, and most of the others. When the universe is quiet, these fields rest at 0, and the vacuum is a place where all of them are sitting calmly at nothing. But one field does not do this. One field is different from every other field in the standard model of particle physics, and its behavior is the reason you have mass, the reason atoms are the size they are, the reason chemistry works the way it does, the reason the universe looks the way it does instead of being an incomprehensible soup of massless particles flying apart at the speed of light. That field is the Higgs field. The Higgs field does not sit at 0 in the vacuum. It sits at a specific non-zero value everywhere in the universe. This is not because something is exciting it. It is not because there is energy being pumped into it from somewhere. It is because the lowest energy state of the Higgs field, its ground state, its version of being completely at rest and undisturbed, is not 0. It is a particular non-zero value. The physics term for this is the vacuum expectation value. The Higgs field has a vacuum expectation value of approximately 246 billion electron volts. That number is set by the shape of the Higgs field's energy landscape, a mathematical structure called its potential. And that non-zero resting value is what gives mass to nearly every fundamental particle in the standard model. But why does the Higgs field sit at a non-zero value? Every other field in the standard model rests at 0 in the vacuum. What makes the Higgs field different? The answer lies in the shape of its potential, the mathematical function that describes how the Higgs field's energy depends on its value. And that shape is unlike anything else in particle physics. For most fields, the energy landscape is simple. Imagine a bowl. The lowest point is at the center. The field value of 0 corresponds to the bottom of the bowl. Move the field away from 0 in any direction, and the energy increases. The field naturally settles at 0 because that is where the energy is lowest. Push the field away and it rolls back. This is the shape of a stable ground state at 0. The Higgs field does not have this shape. Its energy landscape looks more like the bottom of a wine bottle. There is a bump at the center, a raised point where the field value is 0, and around that bump, a circular trough, a valley that runs in a ring around the center. The lowest energy is not at 0. It is in the trough. The field cannot rest at 0 because 0 is actually a local maximum, a hilltop, an unstable point. The field rolls off the bump and settles into the trough at some non-zero value. This is what physicists call spontaneous symmetry breaking. The underlying equations of the standard model are symmetric. They do not prefer any particular direction in the abstract space of the Higgs field. The wine bottle potential is perfectly symmetric around its center, but the actual state of the field, the place where it comes to rest, is not symmetric. The field has to pick a direction in which to roll off the bump, and once it does, the symmetry is broken, not because the laws changed, but because the specific solution, the specific configuration the field chose, does not share the symmetry of the laws that produced it. This is an important conceptual point, and it is worth slowing down to appreciate it. The laws of physics governing the Higgs field are perfectly symmetric. They do not favor any particular vacuum value, but the vacuum itself breaks that symmetry by settling into a specific value. The laws are symmetric. The state is not. And it is the state, not the laws, that determines the physics we observe. The masses of particles, the strengths of forces, the structure of matter, all of these come from the state the Higgs field is in, not from the underlying equations alone. This distinction between the laws and the state, between the equations and the solution, is the conceptual foundation of everything that follows in this episode. Because if the physics we observe comes from a state, and states can change, then the physics we observe is not necessarily permanent. It depends on where the Higgs field sits in its energy landscape. And the question of whether it is sitting at the deepest point in that landscape, or merely a deep point with somewhere deeper still available, becomes the most consequential question in all of physics. The wine bottle shape of the Higgs potential, with its bump at 0 and its trough at 246 billion electron volts, is the shape that the standard model predicts at the energies we can probe directly. It is confirmed by experiment. The Higgs boson, the particle discovered in 2012, is the excitation corresponding to oscillations of the Higgs field around its position in the trough. The mass of the Higgs boson, approximately 125 billion electron volts, corresponds to the curvature of the trough, how steeply the energy rises when the field is displaced from its resting value. Everything about the local shape of the potential is well measured and well understood. But the local shape is not the whole shape. The wine bottle picture describes the potential near where the field sits today. It does not tell us what happens at very high field values, far from the current vacuum. The potential could continue to rise, curving upward forever, ensuring that the current trough is truly the deepest point. Or it could curve back downward at very high values, creating a second, deeper minimum far from where the field currently rests. A minimum that the field has never visited. A minimum that corresponds to a completely different vacuum state with completely different physics. And that is exactly what the standard model calculations suggest when you extend them to high energies. The shape of the Higgs potential, which looks so stable and so well behaved at the energies we can directly measure, appears to develop a second minimum at enormously high field values, a deeper one, a true ground state that the current vacuum, the one we live in, has never reached. Here is how it works. In the equations of quantum field theory, before you account for the Higgs field, many fundamental particles are massless. Electrons, quarks, the W and Z bosons that carry the weak nuclear force, all of them start out in the mathematics with zero mass. If these particles were truly massless, the universe would be unrecognizable. Massless electrons could not be captured into orbits around atomic nuclei. Without electron orbits, there are no atoms. Without atoms, there is no chemistry. Without chemistry, there are no molecules, no solids, no liquids, no gases, no stars as we know them, no planets, no biology, no you. A universe of massless particles is a universe of things moving at the speed of light, never slowing down, never combining, never building anything. The Higgs field prevents that. Because the Higgs field is sitting at a non-zero value everywhere in space, particles that interact with it experience a kind of resistance. Imagine walking through a snowfield. If you're wearing snowshoes, you move on top of the snow with relative ease. If you are wearing regular boots, you sink in and have to push through. And if you are barefoot, you sink even deeper and every step is harder. The Higgs field works on a similar principle for fundamental particles. Particles that interact strongly with the Higgs field, that couple to it intensely, behave as though they have a large mass. Particles that interact weakly with it behave as though they have a small mass. and particles that do not interact with it at all, like photons, remain massless, traveling at the speed of light forever. This is why the top quark, which couples very strongly to the Higgs field, is the heaviest known fundamental particle, roughly 173 billion electron volts. The electron, which couples much more weakly, is far lighter, about 500,000 electron volts. And the photon, which does not couple to the Higgs field at all, has zero mass and always travels at exactly the speed of light in vacuum. This mechanism was proposed in 1964 independently by several groups of physicists. Peter Higgs, working in Edinburgh, published a paper describing the field and predicting that it should have an associated particle, a quantized excitation of the field itself. Francois Englert and Robert Brout, working in Brussels, published a closely related paper the same year. Other physicists, including Gerald Guralnick, Carl Hagen, and Tom Kibble, contributed additional foundational work. Together, these papers established what became known as the Higgs mechanism, the theoretical framework explaining how the Higgs field gives mass to particles through their interaction with its non-zero vacuum value. But for nearly 50 years, the Higgs mechanism was a theoretical proposal, an extraordinarily successful one. The Standard Model predicted particles that were subsequently discovered exactly as predicted. The W and Z bosons, found at CERN in 1983, had masses the Higgs mechanism correctly accounted for. The top quark, discovered at Fermilab in 1995, behaved as predicted. Everything fit. But the Higgs boson itself had never been directly observed. The field was inferred from its effects, like inferring the existence of wind from the way trees bend. That changed on July 4th, 2012. At CERN, the European Organization for Nuclear Research, located near Geneva, Switzerland, 2 independent experiments at the Large Hadron Collider, the largest and most powerful particle accelerator ever built, announced simultaneously that they had discovered a new particle consistent with the Higgs boson. The particle had a mass of approximately 125 billion electron volts. It behaved in the ways the Standard Model predicted a Higgs boson should behave. It decayed into the expected combinations of particles at the expected rates. It was produced in the expected collisions with the expected frequency. After decades of searching, the Higgs boson was real. The Higgs field was confirmed. Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics in 2013 for their theoretical prediction, made nearly half a century earlier. It was one of the longest gaps between prediction and confirmation in the history of physics. And the confirmation required the construction of the most complex and expensive scientific instrument ever built. A 27-kilometer ring of superconducting magnets buried beneath the French-Swiss border, accelerating protons to within a fraction of a percent of the speed of light, and smashing them together billions of times to produce conditions not seen since the first moments after the Big Bang. So, the vacuum of space is not empty. It is the state in which all quantum fields are at their lowest energy. And for the Higgs field, that lowest energy is not zero. The Higgs field is on everywhere, right now, in the space between galaxies, in the void between atoms, in the room you are sitting in. It is sitting at its vacuum expectation value of 246 billion electron volts, silently, invisibly, and it is the reason that electrons have mass, that atoms have structure, that chemistry exists, that stars can form, that you are a solid object instead of a cloud of massless radiation. Everything we consider real Everything we think of as substantial and material and concrete depends on the Higgs field being in this particular state. Not just existing, but being at this particular value. The masses of all the fundamental particles, the strengths of certain forces, the very structure of matter itself, all of it flows from the Higgs field sitting where it sits in its energy landscape. And this is where the story takes its turn. Because the question that physicists started asking after the Higgs boson was discovered, the question that the measured mass of 125 billion electron volts made suddenly urgent, was this. Is the Higgs field sitting at the bottom of its energy landscape? Is the value it holds right now truly the lowest energy state? The absolute ground, the place from which it could never fall any further? Or is it sitting on a ledge? Because in physics, there is a critical difference between a state that is truly stable and a state that merely appears stable. A ball at the very bottom of a valley is truly stable. Push it in any direction and it rolls back to the bottom. There is nowhere lower to go. But a ball resting in a shallow dip partway up a hillside can look stable too. It does not move. It stays where it is. Small disturbances do not dislodge it. For all practical purposes, from the ball's perspective, it is at the bottom, but it is not at the bottom. There is a deeper valley on the other side of the ridge, and if something were to push the ball hard enough, or if through some improbable process the ball were to tunnel through the ridge, it would roll down into the deeper valley and never come back. The shallow dip is what physicists call a false vacuum. It looks like the ground state. It behaves like the ground state. It can persist for extraordinarily long periods, but it is not the true ground state. There is somewhere lower, somewhere more stable, somewhere the fields could fall to if the right conditions were met. And what the measured mass of the Higgs boson suggests, what the calculations of the standard model indicate when you take that mass of 125 billion electron volts and combine it with the measured mass of the top quark and run the equations out to very high energies, is something that should make you pause. The calculations suggest that the Higgs field may not be in the true vacuum. It may be in a false vacuum, a metastable state, a ledge, a shallow dip partway up the energy landscape, with a deeper valley somewhere below it that the field has never fallen into. A valley where the rules of physics would be different, where particle masses would change, where the forces that hold atoms together would operate under different terms. A valley where the universe as we know it could not exist. And the mechanism by which the field could transition from the false vacuum to the true vacuum, the process by which it could fall off the ledge, is one of the most disturbing ideas in all of theoretical physics. It does not require a push. It does not need something to come along and knock it over the edge. Quantum mechanics allows something far stranger. It allows the field to tunnel through the barrier, to appear spontaneously on the other side without ever having had enough energy to climb over. And if that tunneling event were to happen, if a tiny region of space were to suddenly find itself in the true vacuum state, the consequences would not stay contained to that tiny region. They would spread at the speed of light, in every direction, without warning, without any signal that could arrive ahead of them. And what they would carry with them is not destruction in the way you normally think of it, not an explosion, not a shockwave, something worse, a rewriting of the rules, a change in what empty space itself is doing. A new vacuum replacing the old one, volume by volume, with different physics inside it. Physics that does not support the atoms, the chemistry, the biology, or the reality that we depend on. That is the wave in the title of this episode. And understanding what it actually is, how it forms, and why no warning could ever precede it, requires going deeper into the physics of what a false vacuum really means and what happens when one decays. So, we arrived at a question that the discovery of the Higgs boson made suddenly concrete. Is the Higgs field sitting at the absolute bottom of its energy landscape, the true vacuum, the deepest possible state from which it could never fall further? Or is it resting in a false vacuum, a state that looks stable, behaves as though it is stable, but is separated from a deeper, lower energy state by a barrier that quantum mechanics might eventually allow it to cross? To understand why this question matters so much, and why the answer the Standard Model appears to give is so unsettling, we need to understand what metastability really means. Not just as a word, but as a physical condition. Because metastability is not the same as instability. And confusing the two leads to panic that is not warranted, or to complacency that is not earned. An unstable state is one that falls apart the moment it is disturbed. Balance a pencil on its tip and let go. It falls immediately. There is no waiting, no period of apparent calm. The state is unstable, and it collapses at the first opportunity. The universe is clearly not in an unstable state. It has existed for approximately 13.8 billion years. Atoms hold together. Chemistry works, stars burn. If the vacuum were truly unstable, none of this would be here. A stable state is the opposite. It is the true bottom. Disturb it, and it returns to where it was. There is nowhere lower to go. A marble resting at the center of a bowl is in a stable state. Push it, and it rolls back. The state endures because it is genuinely the lowest energy configuration available. A metastable state is something in between. It is not unstable. It does not collapse at the slightest touch. It can endure for enormously long periods, far longer than the current age of the universe. But it is not truly at the bottom either. There is a lower state available, separated from the current one by a barrier. The system remains in the metastable state because the barrier prevents it from reaching the deeper minimum. It is trapped, comfortably, persistently, but not permanently. You have encountered metastability in everyday life without calling it that. Water provides the most intuitive example. Under normal conditions, water freezes at 0 degrees Celsius. But if you cool very pure water very carefully, without vibrations or impurities that could serve as nucleation sites, you can bring the temperature well below 0 without the water freezing. It remains liquid at -5, -10, even -15 degrees Celsius. It looks and behaves like liquid water. You would never guess anything was unusual, but it is not in its true ground state. At those temperatures, ice is the lower energy configuration. The water should be frozen. It is not because the transition to ice requires the formation of an initial seed, a tiny crystal nucleus that the rest of the water can organize around. Without that seed, the water remains trapped in its liquid state, even though a lower energy state is available. It is metastable, and if you disturb it, if you tap the container sharply or drop in a single crystal of ice, the transition happens explosively. The entire volume of supercooled water freezes in seconds, sometimes in a visible wave that sweeps through the liquid. The metastable state collapses into the true ground state, and the transition, once started, cannot be stopped or reversed. The water does not partially freeze. It does not think about it. Once nucleation begins, the entire system falls to its true minimum. This is a useful picture for thinking about what might be happening with the Higgs field, though the consequences in the cosmological case are incomparably more severe than ice forming in your freezer. So how do we know or suspect that the Higgs field might be in a metastable state rather than a truly stable one? The answer comes from the specific numbers that nature has given us. Numbers that physicists measured with enormous care, and that turned out to land in a peculiar and somewhat uncomfortable part of the theoretical landscape. The behavior of the Higgs field at very high energies depends on a quantity called the Higgs self-coupling, often written as the Greek letter lambda. This is the parameter that describes how the Higgs field interacts with itself, and it controls the shape of the Higgs field's energy landscape, its potential. At the energies we can probe directly in the Large Hadron Collider, lambda is positive. The Higgs field's potential has the right shape. It has a minimum at the value where the field sits today, roughly 246 billion electron volts, and everything is well behaved. But quantum field theory requires that you account for what happens when you extend the equations to energies far above what any collider can reach. The coupling constants, the parameters that describe how particles and fields interact, are not truly constant. They change with energy scale. A coupling that is a certain value at low energy can be a different value at high energy. The mathematical machinery that tracks these changes is called the renormalization group, and running the couplings up to high energies is one of the standard and most powerful tools in particle physics. When you run the Higgs self-coupling lambda up to very high energies, something troubling happens. Lambda decreases. It gets smaller as the energy scale increases, and the rate at which it decreases is driven primarily by one particle, the top quark. The top quark is the heaviest known fundamental particle, with a mass of approximately 173 billion electron volts. Because it is so heavy, its coupling to the Higgs field is very strong, and that strong coupling has a large effect on how the Higgs self-coupling evolves with energy. The top quark effectively drags lambda downward. And here is the critical result. For the measured values of the Higgs boson mass, approximately 125 billion electron volts, and the top quark mass, approximately 173 billion electron volts, combined with the measured value of the strong coupling constant alpha s, the Higgs self-coupling lambda appears to cross zero. It goes negative. This happens at an energy scale of roughly 10 to the power of 10 to 10 to the power of 12 billion electron volts, far above anything the Large Hadron Collider can reach, but far below the Planck scale where gravity becomes important. When lambda goes negative, the shape of the Higgs potential changes. The potential that was curving upward, forming a bowl that kept the Higgs field safely in its current minimum, starts curving downward at very high field values. A second, deeper minimum appears at enormously high field values. The Higgs field, in other words, is not sitting at the absolute bottom of its energy landscape. It is sitting in a local minimum with the deeper minimum out there, separated from it by a barrier. This is exactly the structure of a false vacuum. A metastable state. A state that can persist for an extraordinarily long time, but is not the true ground state. The key paper that crystallized this understanding was published in 2012 by a team of physicists including Giuseppe De Grassi, Stefano Di Vita, and several collaborators, using the newly measured Higgs boson mass from the Large Hadron Collider combined with the best available measurements of the top quark mass and the strong coupling constant. They performed a detailed analysis of the Higgs potential at high energies. Their conclusion was stark. The best fit values of the standard model parameters place the electroweak vacuum in the metastable region, not deep in the unstable zone, not safely in the stable zone, but in the narrow metastable band between them. Subsequent analyses by other groups, using increasingly precise calculations with higher order quantum corrections, have consistently confirmed this result. The metastability of the electroweak vacuum is not the conclusion of one paper or one group. It is a robust and repeatedly verified feature of the standard model when extrapolated to high energies. There is an important subtlety here that requires emphasis. The conclusion that the vacuum is metastable depends on the measured masses being exactly what we currently measure them to be, and those measurements have uncertainties. The top quark mass is known to within roughly plus or minus 0.9 billion electron volts. That uncertainty range spans the boundary between the metastable region and the stable region of the Higgs potential. A slightly lighter top quark, by about 2 billion electron volts, could push the vacuum into the absolutely stable regime. A slightly heavier one could push it deeper into metastability. The question of whether the vacuum is metastable or stable has not been settled with absolute certainty. It depends on the precise value of the top quark mass, which is still being refined. But the central values, the best current measurements, favor metastability. And that means we need to take seriously the question of what would happen if the Higgs field were to leave its current metastable state and transition to the deeper minimum. The mechanism by which such a transition could occur was worked out decades before the Higgs boson was discovered, by physicists thinking about the general problem of false vacuum decay in quantum field theory. The foundational work was done by Sidney Coleman, a theoretical physicist at Harvard, in a pair of landmark papers published in 1977. Coleman, and in the second paper his collaborator Curtis Callan, showed that a false vacuum does not decay uniformly. It does not transition smoothly everywhere at once. Instead, it decays through a process called bubble nucleation. Here is how it works, and this is where the physics becomes genuinely extraordinary. In quantum mechanics, there is a phenomenon called tunneling. A particle encountering a barrier that it does not have enough energy to climb over can, with some probability, appear on the other side of the barrier. This is not a metaphor. It is not a figure of speech. It is a measurable, experimentally confirmed property of quantum systems. Electrons tunnel through barriers in every transistor in every computer on Earth. Protons tunnel in the nuclear fusion reactions that power the sun. Alpha particles tunnel out of radioactive nuclei, which is why certain isotopes are radioactive. Tunneling is not exotic or speculative, it is routine physics. Coleman showed that tunneling applies to fields, not just particles. The Higgs field, sitting in its false vacuum state, can tunnel through the energy barrier that separates it from the true vacuum. But the tunneling of a field is not like the tunneling of a single particle appearing on the other side of a wall. When a field tunnels, it does so locally. A small region of space, a tiny bubble, spontaneously transitions to the true vacuum state. Inside the bubble, the Higgs field has dropped to the value of the deeper minimum. Outside the bubble, everything remains in the false vacuum. The bubble wall is the boundary between the two states. The probability of this tunneling event happening at any particular location in any particular moment is spectacularly small. Coleman's calculations showed that the rate of bubble nucleation depends exponentially on a quantity called the bounce action, a number derived from the shape of the energy barrier between the false vacuum and the true vacuum. For the electroweak vacuum with the standard model parameters, the bounce action is enormous, and the resulting probability per unit volume per unit time is correspondingly tiny. How tiny? Calculations performed after the Higgs discovery using state-of-the-art quantum corrections estimate that the lifetime of the electroweak vacuum is on the order of 10 to the power of hundreds of years. One analysis estimated approximately 10 to the power of 790 years. To put that in perspective, the current age of the universe is approximately 10 to the power of 10 years. The estimated vacuum lifetime is not just longer than the age of the universe, it is longer by a factor that has nearly 800 digits. This is a number so large it is difficult to convey in any meaningful way. The probability of the vacuum decaying in any given year, in any given region the size of the observable universe, is so close to zero that for all practical purposes it might as well be zero. But it is not zero. And in physics, the difference between extraordinarily unlikely and impossible is a real and meaningful distinction. In 1980, Coleman extended his analysis in collaboration with Frank Delow-Char. Their paper, titled Gravitational Effects on and of Vacuum Decay, incorporated the effects of general relativity into the bubble nucleation calculation. Gravity, it turned out, changes the picture in important ways. Depending on the energy difference between the true and false vacuums and the properties of the barrier, gravity can either suppress or enhance the tunneling rate. For certain configurations, the Coleman-Delow-Char analysis showed that gravitational effects could make vacuum decay somewhat more likely than the flat space-time calculations suggested. For others, gravity could suppress it entirely, making certain vacuums absolutely stable against tunneling. The detailed interplay between the Higgs potential and gravity at the scales, where the instability appears, remains an active area of theoretical research. The picture that emerges from Coleman's work and its extensions is this. If the electroweak vacuum is metastable, it will eventually decay. Not soon, not on any timescale that any human being should lose sleep over. But eventually, somewhere in the universe, a quantum tunneling event will occur. A tiny bubble of true vacuum will form, smaller than a subatomic particle, and the properties of that bubble, what it does once it forms, are what make this scenario unlike anything else in physics. Now, an essential point must be made here because the distinction between theoretical calculation and experimental observation matters enormously, and recent years have brought developments that sharpen the picture in important ways. For decades, bubble nucleation in vacuum decay was purely a theoretical prediction. Coleman's mathematics described how it should work, but no one had ever seen anything like it in a laboratory. The energies involved in actual Higgs field vacuum decay are so far beyond anything experimentally accessible that direct observation is out of the question. You cannot create a region of true electroweak vacuum in a lab. The energy scales are roughly 10 to the power of 10 billion electron volts, about 1 million times beyond the reach of the Large Hadron Collider. but physicists realized that you can build analog systems, physical systems whose energy landscapes mimic the structure of a false vacuum with a barrier and a true vacuum below it, even though the systems themselves have nothing to do with the Higgs field. If bubble nucleation is a universal feature of quantum systems with metastable states, then it should show up in any system with the right energy landscape, not just the Higgs field. In 2024, a team of physicists in Italy, led by Andrea Zen-Essine and colleagues at the University of Trento, published results in Nature Physics that represented a genuine milestone. They used an ultra-cold gas of sodium atoms, cooled to less than 1/1,000,000th of a degree above absolute zero, and prepared the gas in a metastable magnetic state, a false vacuum analog. The magnetic configuration of the gas had two possible states: a higher energy metastable state and a lower energy ground state, separated by an energy barrier. The researchers watched as bubbles of the lower energy state spontaneously nucleated inside the metastable gas and expanded, exactly as Coleman's theory predicted. The decay rate followed the exponential dependence on the barrier height that the theory demanded. The bubble dynamics matched the theoretical models. This was the first direct experimental observation of false vacuum decay dynamics in a physical quantum system. The researchers were careful to emphasize that their system was an analog. It was a magnetic superfluid, not the Higgs field. The physics of the Higgs vacuum involves energy scales and gravitational effects that no tabletop experiment can reproduce. But the mechanism, the process of quantum tunneling through a barrier followed by bubble nucleation and expansion, was confirmed as physically real. It was not just mathematics. It happened in a laboratory, in front of instruments, on camera. In 2025, a team of researchers used a quantum annealer, a specialized quantum computer with 5,564 superconducting qubits, to simulate false vacuum decay. Published in Nature Physics, the experiment observed quantized bubble formation in real time within a simulated metastable energy landscape. The results showed coherent scaling laws persisting for more than 1,000 intrinsic time units, demonstrating that the process followed predictable quantum mechanical rules even in a complex many-body system. Then, in March of 2026, a team of physicists in China published results in Physical Review Letters, describing an experiment using a ring of Rydberg atoms whose outermost electrons are excited to very high energy levels, to probe false vacuum decay and bubble nucleation. The Rydberg atoms were arranged in a ring with carefully controlled interactions, creating an energy landscape with a metastable state. The researchers observed that the false vacuum decay rate decreased exponentially with the inverse of the symmetry breaking field, directly mirroring the predictions of quantum field theory. They also observed resonant bubble nucleation, a phenomenon where certain bubble sizes are preferentially created due to the discrete energy spectrum of the system, a feature distinctive to quantum systems. These experiments, taken together, represent a remarkable convergence. 3 independent groups, using 3 completely different physical systems, ultra-cold atomic gases, superconducting quantum computers, and Rydberg atom arrays, all observed the same fundamental phenomenon: the spontaneous nucleation of bubbles during the decay of a metastable quantum state. The mechanism that Coleman described mathematically in 1977 is real. It happens. It has been watched, measured, and confirmed to follow the theoretical predictions. But, and this must be stated clearly, None of these experiments say anything about whether the actual electroweak vacuum will decay. They confirm the mechanism. They show that bubble nucleation is a genuine physical process in quantum systems with metastable states. Whether the Higgs field's vacuum is actually metastable depends on details of particle physics at energy scales these experiments cannot touch. Watching supercooled water freeze in a lab tells you that nucleation is real. It does not tell you whether a specific lake somewhere in the world is supercooled and about to freeze. What the experiments do provide is something subtler but important. They remove the escape route of saying that bubble nucleation is just mathematics, just a theoretical curiosity with no physical counterpart. It happens in real quantum systems. If the electroweak vacuum is metastable, then the mechanism by which it would decay is not hypothetical in its nature. It is a demonstrated physical process whose application to the Higgs field is a matter of the specific numbers, not the underlying physics. And this is where the story enters its most disturbing phase, because the question that follows naturally from everything we have discussed is, what would actually happen if a bubble of true vacuum nucleated somewhere in the universe? What would it do? How fast would it expand? What would happen at its boundary? And what would it mean for everything inside it? The answers to those questions are what make false vacuum decay unlike any other threat in the catalogue of cosmic dangers. It is not a collision. It is not a blast. It is not a beam of energy that could, in principle, be shielded against. It is something far more fundamental, something that strikes at the deepest layer of physical reality, the properties of empty space itself. The bubble, once formed, does not sit still. It doesn't remain a tiny region of altered physics contained harmlessly in some remote corner of the cosmos. It grows, and the speed at which it grows, the nature of what it carries with it, and the reason that no warning could ever precede its arrival, those are the subjects of what comes next. A bubble of true vacuum has nucleated. Somewhere, at some point in the universe, a quantum tunneling event has occurred. A region of space smaller than a proton has spontaneously transitioned from the false vacuum state, the one we live in, the one where the Higgs field sits at 246 billion electron volts, to the true vacuum state, the deeper minimum of the Higgs potential. The bubble is unimaginably small. It contains no matter. It is not made of anything in the conventional sense. It is a patch of space where the value of the Higgs field is different, where the rules governing what particles can exist and how they behave have changed. And now comes the part that separates false vacuum decay from every other hypothetical threat in the catalogue of cosmic dangers. The bubble does not stay small. It does not hover in place. It does not dissipate or collapse back into the false vacuum. It grows. And the speed at which it grows is determined by a simple and terrifying piece of physics. The interior of the bubble is in a lower energy state than the exterior. The true vacuum has less energy than the false vacuum. That energy difference is real, and it has to go somewhere. It goes into the bubble wall. The energy released by the transition from false vacuum to true vacuum is converted into the kinetic energy of the expanding wall. The wall accelerates outward, driven by the energy difference between the two vacuum states. And in the absence of friction, in the absence of anything to slow it down, in the absence of any medium that could resist the expansion, the wall accelerates toward the speed of light. Coleman's original calculations showed that in the idealized case, a vacuum bubble wall reaches a velocity asymptotically approaching the speed of light almost immediately after nucleation. The bubble does not gradually pick up speed over years or centuries. The energy difference between the vacuums is so enormous and the wall is so thin that the acceleration is effectively instantaneous on any time scale relevant to human experience. Within a vanishingly small fraction of a second after formation, the bubble wall is moving at very nearly the speed of light. For all practical purposes, it is moving at the speed of light. And here is where the horror of the scenario becomes clear. Think about what it means for something dangerous to approach you at the speed of light. Light is the fastest thing in the universe. Nothing carrying information, no signal, no warning, no observation of any kind can travel faster than light. This is not an engineering limitation that might be overcome with better technology. It is a fundamental law of physics, built into the structure of space-time by Einstein's theory of special relativity. The speed of light is not just the speed at which light happens to travel. It is the speed at which causality itself propagates. It is the maximum speed at which any event in the universe can influence any other event. Now consider what this means for a bubble wall moving at or very near that speed. The bubble forms somewhere. It begins expanding. Light from the bubble wall, photons that might carry information about the wall's existence, begins traveling outward. But the wall itself is moving at essentially the same speed as those photons. The light and the wall are racing neck and neck. The light cannot pull ahead. It cannot arrive at a distant location before the wall does by any meaningful margin. For a wall moving at exactly the speed of light, the photons and the wall arrive simultaneously. You see the wall at the same instant the wall reaches you. There is no gap between the warning and the event. They are the same moment. In practice, the bubble wall approaches the speed of light, but may not reach it with perfect precision. There could be an infinitesimally thin sliver of advance warning, photons arriving a fraction of a second before the wall. But this margin is so small that it is physically meaningless. No detector could register it. No nervous system could transmit a signal from eye to brain in the interval available. The advance warning, to the extent it exists at all, is measured in timescales shorter than the time it takes light to cross a single atom. For every practical purpose, the bubble wall is invisible until it arrives. You cannot see it coming. You cannot detect it approaching. No telescope could spot it because the light that would show it to you is traveling alongside it, arriving at the same moment. No gravitational wave detector could sense it in advance, because gravitational information also propagates at the speed of light. No instrument of any kind, based on any technology, exploiting any physical phenomenon, could provide warning. The laws of physics themselves forbid it. This is fundamentally different from every other cosmic threat you have ever heard of. An asteroid heading toward Earth can be seen years in advance. A gamma ray burst travels at the speed of light, but astronomers can identify candidate stars. A nearby supernova would announce itself through neutrinos arriving slightly before the light. Even a black hole drifting through the solar system would betray its presence through gravitational effects on planetary orbits. Every one of these dangers comes with some form of warning, some window in which the approaching threat is knowable. A vacuum decay bubble provides none of that. Zero warning. The first moment you could, in principle, learn of its existence is the moment it has already arrived. And by then, the word you has already stopped meaning anything, because the physics that allows you to exist has been overwritten. Which brings us to the most important and most misunderstood aspect of the entire scenario. What happens inside the bubble? what the wall actually does when it reaches a region of space. Because this is where most people's intuitions go wrong, and correcting that intuition is essential to understanding why false vacuum decay is not just another apocalypse scenario. When most people imagine a wave destroying everything, they picture a blast wave from an explosion, a wall of force that slams into objects and breaks them apart. The objects are shattered but still there. The atoms are scattered but still there. The laws of physics are the same, just applied violently. Things are pushed, crushed, torn, heated, vaporized. But the fundamental building blocks survive. They just get rearranged. A vacuum decay bubble does not work this way. It is not a blast wave. It does not push things. It does not shatter objects through force. What it does is far more radical and far more final. It changes the vacuum state. It changes what empty space is doing. And because the properties of every particle in the universe depend on what the vacuum is doing, changing the vacuum changes everything. Remember what we established earlier. The masses of fundamental particles are not intrinsic properties of the particles themselves. They are consequences of how those particles interact with the Higgs field, and specifically with the Higgs field's vacuum expectation value. The electron has the mass it has because the Higgs field is sitting at 246 billion electron volts. If the Higgs field were sitting at a different value, the electron would have a different mass, the quarks would have different masses, the W and Z bosons would have different masses. Every particle whose mass comes from the Higgs mechanism would be different. Inside the vacuum decay bubble, the Higgs field is at a different value, the true vacuum value. We do not know exactly what that value is, because the detailed shape of the Higgs potential at the enormously high field values where the true minimum sits is sensitive to physics we have not fully worked out. But we know it would be at a field value enormously larger than 246 billion electron volts. Deep in a regime where the fundamental constants governing particle masses and forces would be radically different from what we experience. In that regime, the masses of all the fundamental particles change, and when the masses of fundamental particles change, everything built out of those particles ceases to function. Consider what happens to an atom. An atom is a nucleus of protons and neutrons surrounded by a cloud of electrons. The size of the atom, the radius of the electron cloud, is determined by a balance between the electromagnetic attraction pulling the electron toward the nucleus and the quantum mechanical properties of the electron that prevent it from collapsing into the nucleus. Those quantum mechanical properties depend on the electron's mass. Change the electron's mass, and the balance shifts. The atom changes size, or if the mass changes enough, the balance breaks entirely. Electrons can no longer form stable orbits. Atoms as we know them cease to exist. But it is even worse than that. The masses of the up and down quarks, the quarks that make up protons and neutrons, also come from the interaction with the Higgs field. Change the Higgs field's value, and you change the quark masses. Protons and neutrons are bound, states of quarks held together by the strong nuclear force. The stability of the proton, the fact that it does not decay, depends on a delicate relationship between the masses of the up quark, the down quark, and the electron. If those masses change, the proton might become unstable. It might decay spontaneously into lighter particles. Neutrons, which are already unstable outside of nuclei and decay, with a half-life of about 10 minutes, would have their decay properties altered as well. Nuclear physics, the physics that determines which elements can exist, and which nuclei are stable, would be completely rewritten. Let us trace this cascade more carefully, because the specifics matter. They are what separate a vague claim that everything changes from a grounded understanding of exactly how matter comes apart when the vacuum state shifts. Start with nuclear binding energy. Right now, protons and neutrons are held together in atomic nuclei by the strong nuclear force, mediated by particles called gluons. The binding energy of a nucleus, the energy required to pull it apart into individual protons and neutrons, depends on a delicate balance between several competing effects. The strong force attracts nucleons to each other. The electromagnetic force causes protons to repel each other. The masses of the up quark and the down quark determine the masses of the proton and neutron, and the small difference between the proton mass and the neutron mass, approximately 1.3 million electron volts, is critical. That tiny mass difference is the reason the universe has the chemistry it has. Because the neutron is slightly heavier than the proton, free neutrons are unstable. They decay into protons, electrons, and antineutrinos with a half-life of about 10 minutes. This is mediated by the weak nuclear force, but inside a nucleus, the binding energy can stabilize neutrons, preventing them from decaying. The specific elements that can exist, the periodic table as we know it, is a consequence of this mass difference combined with the binding energies set by the strong force and the repulsion set by the electromagnetic force. Change the quark masses, which is what a shift in the Higgs vacuum value would do, and this balance breaks. If the down quark became lighter than the up quark, the proton would become heavier than the neutron instead of the other way around. The proton would then be the unstable particle, decaying into a neutron, a positron, and a neutrino. Hydrogen, the most abundant element in the universe, is a single proton with an electron orbiting it. If protons were unstable, hydrogen could not exist on cosmological timescales. Without hydrogen, there was no water. Without hydrogen, the primary fuel for stellar fusion is gone. Stars as we know them could not form. The cascade from a shift in quark masses to the elimination of the most abundant element in the universe, to the shutdown of stellar physics, to the end of chemistry is direct, concrete, and unavoidable. But even if the quark masses shifted in a direction that kept the proton stable, the nuclear binding energies would change. The binding energy per nucleon varies across the periodic table. Light elements like hydrogen and helium have lower binding energy per nucleon. Iron has the highest. Elements heavier than iron have progressively lower binding energy, which is why nuclear fission of heavy elements releases energy and nuclear fusion of light elements releases energy, both sliding toward the iron peak. This entire landscape of nuclear stability depends on the specific strengths of the forces involved and the specific masses of the particles. Change those masses and the landscape reshapes. Elements that are currently stable might become unstable. Elements that are currently unstable might become stable. The periodic table would not just lose a few entries, it would be replaced by an entirely different table, with different stable nuclei, different radioactive isotopes, different chemistry. And chemistry is the next domino. Chemical bonds, the connections between atoms that create molecules, depend on the electromagnetic force and the quantum mechanical properties of electrons. The length of a chemical bond, the angle between bonds, the energy required to break a bond, all of these are set by the mass of the electron, the charge of the electron, and the constant that describes the strength of the electromagnetic interaction. In the current vacuum, These values produce the rich and specific chemistry that allows molecules like water, amino acids, proteins, and DNA to exist. Each of these molecules has a structure that depends on bond lengths and bond angles, and bond energies being within very specific ranges. A shift in the Higgs vacuum value would change the electron mass. Even a modest change, a factor of 2 or 3, would be devastating for chemistry. Molecular bond lengths would change. The energy levels of electrons in atoms would shift. Some molecules that are currently stable would become unstable. Others that cannot form under current conditions might become possible. But the specific chemistry that produces water, that allows carbon to form 4 bonds in the tetrahedral geometry, that makes organic chemistry possible, that permits the hydrogen bonds holding DNA's double helix together, all of that depends on the electron mass being what it currently is. Change it, and you do not get slightly different chemistry. You get alien chemistry. Chemistry that has no particular reason to support the molecular structures that biology requires. And we have not yet considered what happens to the forces themselves. If the Higgs field shifts to an enormously high value, the W and Z bosons, whose masses are proportional to the Higgs vacuum value, become extraordinarily heavy. The weak nuclear force, which in our vacuum already operates only over distances smaller than an atomic nucleus, would shrink to an even tinier range, altering radioactive decay and the nuclear reactions that power stars. Meanwhile, the masses of all quarks and leptons would scale up dramatically, making every fundamental particle far heavier than it is today. Electrons that are currently light enough to form extended orbital clouds around nuclei would become so massive that atomic structure as we know it could not exist. The delicate balance of forces and masses that produces our periodic table, our chemistry, our biology, would be obliterated, not by the removal of forces, but by their distortion beyond any configuration compatible with the structures we depend on. The cascade runs all the way down through every scale of physical structure. Quark masses set nuclear stability. Nuclear stability sets the periodic table. The periodic table sets chemistry. Chemistry sets molecular biology. Molecular biology sets life. Each level depends on the one below it, and every level below ultimately depends on the vacuum expectation value of the Higgs field. Move the Higgs field to a different value, and you do not remove one link in the chain. You replace the entire chain with a different one. One that has no particular reason to support atoms as we know them, molecules as we know them, stars as we know them, or life in any form we would recognize. This is what end everything means. Not an explosion that shatters the world into pieces that could, in principle, be reassembled. A change in the rules that makes the pieces themselves impossible. The bubble wall does not destroy matter. It makes matter, as we define and experience it, a concept that no longer applies. The picture that emerges is not one of destruction in any familiar sense. It is not that the bubble wall hits atoms and breaks them. The atoms are not hit by anything. There is no force, no impact, no collision. What happens is that the rules change. The fundamental constants that determine how particles behave, how forces operate, how matter holds together, are replaced by different values. Values that do not support the structures we know. The atoms do not break. They simply cannot exist in the new vacuum. The chemistry does not fail because something interferes with it. It fails because the conditions that allowed it are no longer present. Think of it this way. Imagine you're playing a board game. You know the rules. You have a strategy. Your pieces are on the board in positions that make sense given the rules you're playing by. Now imagine that someone swaps the rule book. Not gradually, not one rule at a time. All at once. Every rule changes simultaneously. The board is the same. The pieces are in the same positions. But the rules that govern what those pieces can do, how they interact, what constitutes a legal move, all of that has been replaced. Your strategy is meaningless. Your positions make no sense. The game you are playing no longer exists. Not because someone knocked the board over, because the game itself changed. That is what happens inside a vacuum decay bubble. The board is space-time. The pieces are particles. The rules are the laws of physics as determined by the vacuum state. And the bubble wall is the moment when every rule changes at once. There is another way to think about why matter cannot survive the transition. Every particle in our universe is, as we discussed, an excitation of a quantum field. And those excitations, those vibrations, are tuned to the current vacuum. They exist because the current vacuum supports them. An electron is a specific mode of excitation of the electron field in the current vacuum state. It has the properties it has, because the vacuum has the properties it has. In a different vacuum, the electron field would have different properties. The modes of excitation it supports would be different. An electron as we know it might not be a valid excitation of the electron field in the new vacuum. It would be like a radio tuned to a specific frequency. The signal comes in clearly because the radio is matched to the broadcast. Now change the broadcast frequency. The radio does not explode. It does not melt. It simply receives static. The signal it was built to receive no longer exists. The electron in the new vacuum is static. It is not a valid state. It does not persist. What replaces it, if anything, depends on the physics of the true vacuum. There might be particles in the true vacuum. There might be forces. There might even be some form of structure. But it would be structure governed by completely different rules. Different masses, different force strengths, different stable configurations. It would be as foreign to us as our universe would be to whatever exists there. Two entirely different sets of physics sharing the same space-time, separated by a wall moving at the speed of light. This is why the phrase "end everything" in the title does not mean what it usually means in popular descriptions of cosmic disasters. It does not mean that everything is smashed. It means that everything is replaced. The physical conditions that allow matter, chemistry, stars, planets, oceans, atmospheres, cells, DNA, thought, sensation, experience, all of it. Those conditions are properties of the current vacuum. Change the vacuum and those conditions vanish. Not violently, not explosively, simply, completely, irrecoverably. Now, having described something this horrifying, there is a critical question that must be addressed honestly and thoroughly. Could we trigger this? Could a particle collider, a nuclear weapon, a cosmic ray, or any human-made event create a vacuum decay bubble? The short answer is no. And the reason is not speculative or based on wishful thinking. It is based on observational evidence that is as strong as evidence gets in physics. The concern that high-energy particle collisions might trigger vacuum decay has been raised and addressed repeatedly, most formally in the safety assessments conducted before the Large Hadron Collider began operations. The LHC Safety Assessment Group published a detailed review in 2008, examining all hypothetical catastrophic scenarios associated with high-energy collisions, including vacuum decay. Their conclusion was unambiguous. The collisions produced by the Large Hadron Collider pose no danger. The argument is elegant and rests on a simple observational fact. The Large Hadron Collider is not the most powerful particle accelerator in the universe. It is not even close. Nature has been running far more powerful collisions for billions of years. Cosmic rays, high-energy particles accelerated by supernovae, active galactic nuclei, and other violent astrophysical processes strike objects throughout the universe at energies that dwarf anything the Large Hadron Collider can achieve. The highest energy cosmic rays ever detected carry energies of roughly 10 to the power of 20 electron volts. The Large Hadron Collider operates at a center of mass energy of approximately 13 trillion electron volts, which is 10 to the power of 13 electron volts. The most energetic cosmic rays exceed this by a factor of 10 million. These cosmic rays have been striking the Earth, the Moon, the Sun, neutron stars, white dwarfs, and every other dense astronomical body in the observable universe for billions of years. Every second, high-energy cosmic ray protons slam into atoms in Earth's upper atmosphere, at energies far exceeding the Large Hadron Collider's capability. Each of these collisions is a miniature particle physics experiment, producing the same kinds of particles and the same kinds of extreme conditions that the Large Hadron Collider creates. And here is the key point. The Earth still exists. The Sun still exists. Neutron stars, which are struck by cosmic rays at even higher rates because of their stronger gravity, still exist. White dwarfs, which have existed for billions of years and have been bombarded by cosmic rays for that entire time, still exist. If high-energy particle collisions could trigger vacuum decay, they would have done so already. Not once, but countless times, at energies far beyond anything humans can produce. The continued existence of dense astrophysical objects that have been subjected to high-energy cosmic ray bombardment for billions of years is direct observational evidence that such collisions do not trigger vacuum decay. This is not a theoretical argument, it is an empirical one. Nature has already performed the experiment. The universe has been running high-energy particle collisions against dense targets for longer than the Earth has existed. The result is clear. Those collisions do not produce vacuum decay bubbles. If they could, the universe would already be gone. It is worth being specific about the energies involved, because the numbers are striking, and they make the safety argument not just persuasive, but overwhelming. On October 15th, 1991, the Fly's Eye detector in Utah recorded a single cosmic ray particle with an energy of approximately 320 billion electron volts. This became known as the "Oh my God" particle, named for the reaction of the physicists who measured it. To put that energy in context, this single subatomic particle, probably a proton, carried the kinetic energy of a baseball thrown at about 60 miles per hour. All of that energy compressed into a single proton. The Large Hadron Collider, the most powerful collider ever built, produces collision energies of 13 trillion electron volts. The Oh my God particle carried roughly 25 million times more energy than the Large Hadron Collider produces. And the Oh my God particle was not unique. Ultra-high energy cosmic rays at energies above 1 billion electron volts strike the Earth's atmosphere at a rate of roughly 1 per square kilometer per year. That sounds modest, but integrated over the entire surface of the Earth, it means the Earth is hit by hundreds of millions of such particles every year. Over the 4.5 billion years the Earth has existed, the total number of ultra-high energy cosmic ray impacts on Earth alone is beyond counting. Now extend this to other objects. The Sun is much larger than the Earth. Its cross-sectional area for collecting cosmic rays is roughly 12,000 times greater. The Sun has existed for approximately 4.5 billion years. The number of ultra-high energy cosmic ray impacts on the Sun over its lifetime is staggering, orders of magnitude beyond the Earth's total. Neutron stars are even more important for this argument. A neutron star is the collapsed core of a massive star, roughly 12 miles across but containing 1 to 2 times the mass of the Sun. Neutron stars have surface gravities roughly 200 billion times stronger than Earth's. This means they gravitationally focus incoming cosmic rays, dramatically increasing the rate at which they are struck. Moreover, because neutron stars are so dense and so massive, any product of a collision, any hypothetical dangerous particle or vacuum bubble seed, would be gravitationally trapped. It could not escape. It would be held inside the neutron star by the most extreme gravitational field of any known object outside a black hole. The Milky Way alone contains an estimated 100 million to 1 billion neutron stars, and there are hundreds of billions of galaxies in the observable universe. The total number of neutron stars is staggering beyond easy comprehension. Many of them are billions of years old. They have been pelted by cosmic rays at energies exceeding anything the Large Hadron Collider can produce for their entire existence. Every single one of them still exists. None has been consumed by a vacuum decay bubble. None has vanished. None has shown any sign of the catastrophic phase transition that vacuum decay would produce. The evidence is not ambiguous. It is absolute. Nature has performed trillions upon trillions of experiments at energies millions of times higher than our most powerful collider, against targets billions of times denser than anything on Earth, and the result is the same every time. Nothing happens. The vacuum holds. White dwarfs provide yet another line of evidence. A white dwarf is the remnant core of a dead star, roughly the size of Earth, but with a mass comparable to the Sun. White dwarfs are ancient. Some of the oldest known white dwarfs in our galaxy are approximately 11 to 12 billion years old. They have been accumulating cosmic ray impacts for nearly the entire history of the Milky Way. They are dense enough to trap any collision products. And they still exist, quietly cooling in the galactic disk, undisturbed by the countless high-energy impacts they have absorbed. The safety argument from astrophysical observations is not a speculation about what might be true. It is a direct reading of the evidence. The universe has been testing the vacuum against high-energy collisions for billions of years, at energies and rates and densities that dwarf anything human beings will ever produce. The result of that test is the continued existence of every dense object in the observable universe. The vacuum has passed every test nature has thrown at it. That is a subtlety sometimes raised in more careful discussions. Someone might object that the conditions in a particle collider are different from cosmic ray collisions in ways that matter. For instance, in a collider, two beams of particles traveling in opposite directions collide head-on, producing a center of mass frame that is stationary relative to the laboratory. In a cosmic ray collision, one particle is moving at high speed and strikes a stationary target, producing a center of mass frame that is itself moving at high speed relative to the target. Could this difference matter? The safety analysis addressed this. Even accounting for the different kinematics, what matters for vacuum decay is the total energy available in the center of mass frame, and cosmic rays provide that energy in abundance. The fact that cosmic ray collisions happen against astrophysical bodies that gravitationally retain whatever is produced means that any dangerous product would be trapped inside those bodies. The survival of those bodies over billions of years rules out the scenario. Furthermore, the energy scale at which the Higgs potential appears to develop its instability is on the order of 10 to the power of 10 billion electron volts or higher. This is roughly 1,000,000 times the energy of the Large Hadron Collider. And while the most energetic cosmic rays carry enormous total energy in the lab frame, what matters for particle physics is the energy available in the center of mass frame of the collision, which is far lower. Even the oh my god particle, colliding with a stationary proton, produces a center of mass energy tens of thousands of times below the instability scale. The energies involved in potential vacuum decay are not in the neighborhood of anything that occurs naturally in particle collisions in the current universe. So false vacuum decay, if the electroweak vacuum is indeed metastable, is something that would happen spontaneously through quantum tunneling, not through any collision or event that concentrates energy at a point. It is a random quantum fluctuation occurring with a probability so low that the expected wait time dwarfs the current age of the universe by hundreds of orders of magnitude. It cannot be triggered by a particle accelerator. It cannot be triggered by a supernova. It cannot be triggered by two neutron stars colliding. It is not something that human activity or even violent cosmic events could cause. This should be reassuring. And in a practical sense, it is the probability that vacuum decay will happen tomorrow, or this year, or in the next billion years, or in the next trillion years is so small that it is essentially zero by any human standard of concern. If you are looking for things to worry about, asteroid impacts, climate change, pandemic disease, nuclear conflict, all of these rank immeasurably higher on any rational list of threats. False vacuum decay is not something that keeps physicists up at night in a practical sense. It is not an active threat. It is not an approaching danger. It is a theoretical possibility with a probability so low that it borders on the meaningless for any individual or civilization. And yet the concept disturbs in a way that no other cosmic threat does. Not because it is likely, not because it is imminent, not because anyone should be afraid in the moment-to-moment, practical sense of the word. It disturbs because of what it reveals about the nature of reality itself. Because if the electroweak vacuum is metastable, then everything, every atom, every star, every living thing, every law of chemistry and biology that we depend on, all of it rests on a state of empty space that is not guaranteed to be permanent. Not by any principle, not by any law, not by any cosmic promise. The universe we know, the one with atoms and stars and people, exists because the Higgs field happens to be sitting at a particular value. Not because that value is sacred, not because the universe was designed to maintain it, simply because quantum tunneling has not yet carried the field to a lower state. The rules of physics that allow us to exist are not written in stone. They are written in the vacuum. And the vacuum, according to the best calculations available, might be a draft rather than a final version. That is the weight of this idea. Not the probability, which is negligible, not the timing, which is unimaginably remote, but the implication, the suggestion that physical reality as we know it is conditional, that it depends on a quantum state whose permanence is a question, not an answer, that the solidity of the world, the reliability of the forces, the stability of atoms, all of the things you take for granted every second of every day, might be features of a metastable configuration rather than properties of the universe's deepest ground state. And it is that implication, that philosophical weight, that requires one final reckoning. Because the question is no longer about whether the bubble will come, or how fast it would move, or what it would do to atoms. The question, the real question, is what it means to live in a universe where the ground beneath physics itself might not be the true ground. Let us be honest about what we know and what we do not. We do not know that the electroweak vacuum is metastable. The calculations that point to metastability are the best we have. They use the most precise measurements of the Higgs boson mass, the top quark mass, and the strong coupling constant available. They incorporate quantum corrections computed to extraordinary precision by some of the most capable theoretical physicists alive. And they consistently land in the metastable region of the parameter space, not deep in it, not at the extreme edge, but squarely in the zone where the vacuum appears long-lived, but not eternal. These calculations are serious. They are not fringe. They are not speculative in the way that string theory landscapes or multiverse proposals are speculative. They follow directly from the standard model of particle physics, the most successful and thoroughly tested theory in the history of science, applied to the specific numbers that nature has provided. But the conclusion depends on those numbers being exactly right. And they are not exactly right. They are right to within measurement uncertainties, and those uncertainties, particularly on the top quark mass, are large enough to matter. The top quark mass is the single most important input for determining whether the vacuum is stable or metastable. A top quark mass of approximately 171 billion electron volts would place the vacuum firmly in the stable region. A mass of approximately 175 billion electron volts would push it deeper into metastability. The current best measurement is approximately 173 billion electron volts, with an uncertainty of roughly plus or minus 0.9 billion electron volts. That uncertainty window straddles the boundary. The answer to one of the most profound questions in fundamental physics, whether the ground state of the universe is truly stable, depends on a measurement that is not yet precise enough to settle it. Future experiments may resolve this. Proposed next-generation colliders, including the International Linear Collider and the Future Circular Collider, would be capable of measuring the top quark mass with far greater precision, potentially narrowing the uncertainty to a few 100 million electron volts or less. At that level of precision, the question of vacuum stability could be answered definitively within the framework of the standard model. We would know whether the Higgs self-coupling truly crosses zero at high energies, or whether it stays positive, keeping the vacuum safely in the stable regime. But there is a deeper issue, and it is one that no collider can resolve by itself. The standard model might not be the complete picture. The standard model is extraordinarily successful, but physicists have strong reasons to believe it is not the final theory of nature. It does not include gravity in a quantum mechanical framework. It does not explain dark matter or dark energy. It does not explain why there is more matter than antimatter. It does not explain the specific values of its own parameters, the particle masses and coupling constants that it takes as inputs, rather than deriving from deeper principles. If there is physics beyond the standard model, and almost all physicists believe there is, then that new physics could affect the stability of the vacuum in ways that the standard model alone cannot predict. New particles at high energy scales would modify the running of the Higgs self-coupling. They could stabilize the vacuum, preventing lambda from ever crossing zero. Or they could destabilize it further, making the metastable region deeper or the barrier lower. Without knowing what the new physics is, we cannot know how it affects the vacuum. This is a genuinely open question. The vacuum might be absolutely stable, protected by new particles or symmetries that the standard model does not contain. Or it might be metastable exactly as the standard model predicts. Or it might be worse than the standard model suggests, with additional instabilities introduced by new fields we have not yet detected. We do not know, and that ignorance is itself part of the story. What we can say with confidence is this: if the vacuum is metastable, its lifetime is extraordinarily long. The most careful calculations place it at approximately 10 to the power of 790 years. Let that number settle in for a moment. The current age of the universe is approximately 13.8 billion years, which is roughly 10 to the power of 10 years. The estimated vacuum lifetime exceeds the age of the universe by a factor that would take hundreds of digits to write out. The probability that the vacuum will decay in any given year, anywhere in the observable universe, is so small that there is no meaningful analogy for it. It is not like the odds of winning a lottery. It is not like the odds of being struck by lightning. It is smaller than the odds of any event you have ever contemplated, by a margin that makes comparison absurd. Even over timescales far longer than the current age of the universe, the probability remains negligible. If the universe continues to exist for 1 trillion years, 100 trillion years, the expected probability of vacuum decay having occurred remains essentially zero compared to the estimated lifetime. The vacuum, if metastable, is metastable in the most extreme sense imaginable. It is not going anywhere anytime soon. Not on any timescale that any civilization, any species, any star, or any galaxy will ever experience. And yet the concept refuses to be fully tamed by those numbers. Part of the reason is mathematical. A probability that is extraordinarily small but non-zero is fundamentally different from a probability that is zero. In a universe that might be spatially infinite, even an incredibly small probability per unit volume per unit time eventually produces an event somewhere. If the universe is truly infinite in extent, then somewhere, at some incomprehensibly distant location, a bubble may already be nucleating. It would never reach us. It would be separated from us by distances so vast that the expansion of the universe would carry us apart faster than the bubble could grow. We would never know about it. It would exist in a causally disconnected region, affecting nothing we could ever observe. But the logical structure of the idea that the transition might already be happening somewhere is inherent in the mathematics of a spatially infinite universe with a non-zero decay rate. It is not a threat. It is a structural feature of the theory. But the deeper reason the concept is unsettling has nothing to do with probabilities at all. It has to do with what the concept reveals about the nature of the reality we inhabit. We live our lives as though the laws of physics are permanent. Gravity works today the same way it worked yesterday. The speed of light has not changed since breakfast. The mass of an electron is the same now as it was 1 billion years ago. The universe behaves with a consistency so total that we have built entire civilizations on the assumption that the rules do not change. Science itself depends on this assumption. If the laws of physics varied randomly from place to place or moment to moment, observation would be meaningless and prediction futile. The fact that experiments are repeatable is evidence that the laws of physics are, at minimum, extraordinarily stable. But false vacuum decay raises the possibility that this stability, this magnificent reliability, is not a feature of the universe's deepest structure. It might be a feature of its current state, a state that could, in principle, change. Not because something breaks the laws, not because some external force disrupts them, but because the laws themselves emerge from a vacuum configuration that is not the true ground. The stability we depend on would be, in this picture, the stability of a metastable state. Real, robust, effectively permanent on any human timescale, but not fundamental, not guaranteed, not written into the architecture of reality at the deepest level. This is a strange kind of vertigo. It is not the vertigo of standing at the edge of a cliff, looking down at a fall that might kill you. It is the vertigo of discovering that the ground you are standing on, the ground you always assumed was bedrock, might be a layer of sandstone over a cavern. The sandstone is strong. It is held for billions of years. It shows no signs of giving way. Every test you can perform says it is solid. But the knowledge that it is not the deepest layer, that there is something beneath it, changes how you feel about the ground, even if nothing about the ground itself has changed. The physicist who understands false vacuum decay does not walk differently, does not weigh more or less, does not experience the universe as less real or less reliable. The atoms in their body are held together by the same forces, governed by the same constants, obeying the same equations as they would if the vacuum were absolutely stable. Nothing about their immediate physical experience is altered by the knowledge, and yet the knowledge matters. It matters because it reframes what physical reality is. It transforms the laws of physics from permanent features of an eternal universe into emergent properties of a contingent state. Properties that are spectacularly stable, unfathomably long-lived, but ultimately dependent on a quantum field configuration that might not be the last word. There is something worth pausing on in the peculiar location where the measured parameters place us. The Higgs boson mass and the top quark mass, taken together, put the standard model vacuum not deep in the stable region, and not deep in the metastable region, but right near the boundary between them. The vacuum, if metastable, is only barely metastable. The Higgs self-coupling barely crosses zero, and it does so at an energy scale enormously far above anything we can probe directly. The barrier between the false vacuum and the true vacuum, if it exists, is wide and tall. The lifetime is staggeringly long. The system is as close to stable as a metastable system can be without actually being stable. Some physicists find this near criticality suggestive. Why should the parameters land so close to the boundary? If they were random, you might expect them to be deep in one region or the other. The fact that they sit near the edge might be a coincidence, or it might be a clue. Some theoretical frameworks, including certain versions of the multiverse hypothesis and the principle of asymptotic safety, predict or accommodate vacuum states near the stability boundary. The near criticality might be telling us something about the deeper structure of the theory, something we do not yet understand. Or it might be telling us nothing at all, just an accident of the particular values that nature happened to choose. We do not know. It is one more open question in a subject full of them. What we are left with after all the calculations and all the experiments and all the theoretical frameworks is something irreducibly simple and irreducibly uncomfortable. The universe we inhabit, with its atoms and stars and people, depends on the Higgs field being in a particular state. That state appears to be metastable. It has an estimated lifetime so long that human language does not have words for the numbers involved. The probability of it changing on any time scale that matters to anyone is so close to zero that worrying about it in any practical sense would be irrational. But the concept itself, stripped of the numbers, stripped of the probabilities, stripped of the reassurances, is this. The reality we live in might not be the deepest version of reality. The physical rules that we depend on for our existence might be properties of a temporary state rather than permanent features of the universe. And the transition from this state to a deeper one, if it ever occurred, would be total, would be final, and would arrive without any possibility of warning, because the boundary of the transition would move at the speed of light, and nothing at all can outrun that. This is not a threat in the practical sense. It is not something to fear in the way you fear disease or disaster or the ordinary fragilities of human life. Those are real. Those deserve your attention. False vacuum decay does not in any practical way, but it is something to reckon with in a deeper sense, because it touches on the question of what the universe is at its most fundamental level. And the answer it suggests is that the universe, at its most fundamental level, might be contingent, dependent on a state of affairs that is not logically necessary, not guaranteed by any principle, not protected by any cosmic law. We are accustomed to thinking of the laws of physics as the bedrock of reality, as the things that cannot change, the foundation on which everything else is built. Matter can be created and destroyed. Stars can be born and die. Civilizations can rise and fall. But the laws, the deep rules, those are eternal. Those are fixed. Those are the one thing you can always count on. False vacuum decay suggests otherwise. It suggests that the laws themselves, or at least the specific version of them that we experience, are products of a vacuum state. And vacuum states, in quantum field theory, can change. Not easily. Not quickly. Not on any time scale that should concern you personally. But they can change. The rules of the game are not carved into the fabric of existence itself. They are written in the vacuum. And the vacuum is a physical system, subject to the same quantum mechanical principles as everything else. There is a way of reading this that is purely negative. That sees it as one more reason the universe is indifferent, one more way in which existence is fragile, one more argument for cosmic despair. Everything you care about, everything that has ever existed, depends on a field configuration that nobody chose and nobody controls. And if that configuration were to change, there is nothing anyone could do about it. But there is another way to read it. And I think this reading is truer to the spirit of the physics. The fact that we can ask this question at all is extraordinary. The fact that human beings, made of atoms, made of particles whose masses are set by the Higgs field's vacuum value, can look at the Higgs field and ask whether its vacuum value is truly stable. That is a remarkable thing. We are not just products of the vacuum, we are the part of the vacuum that understands itself. We are the quantum fields looking at their own ground state and asking whether it is the true ground. No other structure in the known universe does this. No star asks whether the nuclear physics that powers it might be contingent. No galaxy wonders whether the gravitational constant that holds it together could change. Only matter organized into the particular configuration that we call conscious life can pose the question. And posing the question, even if the answer is unsettling, is not nothing. It is arguably the most significant thing that matter has ever done. The universe did not have to produce beings capable of understanding vacuum metastability. The laws of physics, whatever their ultimate status, did not require that their own contingency be recognized. But it happened. Here on this planet, in this thin sliver of cosmic time, matter organized itself into forms that could look at the deepest structure of reality and notice the crack. Not a crack in the wall, not a crack in the floor, a crack in the concept of permanence itself. And that recognition, that awareness that the ground beneath physics might not be the final ground, is not a cause for despair. It is a cause for something closer to awe, because it means that the universe we inhabit, the one with atoms and stars and people and music and thought, is not inevitable. It is not guaranteed. It is not the only possible version. It is a particular arrangement of fields in a particular state, producing a particular set of rules, enabling a particular kind of complexity. And that complexity, against all odds, has become aware of its own contingency. The wave in the title is real in the sense that the physics behind it is real. False vacuum decay is a genuine prediction of quantum field theory, grounded in the same mathematics that correctly predicted the existence and properties of the Higgs boson decades before it was discovered. The mechanism of bubble nucleation has been confirmed in laboratory analogues. The measured parameters of the standard model place the vacuum in a region consistent with metastability. None of this is fiction. None of it is speculation dressed up as science. It is the direct output of the best tested physical theory humanity has ever produced, applied to the specific numbers that experiments have measured. But the wave is not approaching. It is not on its way. There is no evidence that a vacuum decay bubble has formed anywhere in the observable universe. There is no reason to expect one to form in the lifetime of any star currently burning. There is no instrument that has detected a signal, no observation that has raised an alarm, no theoretical development that has shortened the estimated timescale from its current absurd length. The wave is a possibility, not prophecy, a conditional statement, not a prediction, an if, not a when. And the horror of it, such as it is, lies entirely in the if, in the fact that the word applies at all, in the discovery that the laws of physics, which feel so solid and so permanent and so non-negotiable, might be written in an ink that could fade, not soon, not perceptibly, not in any way that matters to the beating of your heart or the turning of the earth or the burning of the sun, but in principle, in theory, in the quiet mathematics that runs beneath everything. The universe is not ending. The vacuum is not collapsing. No wave is approaching. You are safe in every practical sense of the word from this particular scenario. And you should hold that truth firmly, because it is true. But you should also hold the other truth, the stranger one, the one that sits quietly beneath the first. The truth that the most frightening wave imaginable would not be one that travels through the universe destroying things. It would be one that travels through the universe replacing things, replacing the vacuum, replacing the rules, replacing the conditions that allow atoms and stars and thought to exist with different conditions that do not, moving at the speed of light, carrying no warning ahead of it because no warning could travel faster than it does. Arriving not as a wall of fire or a wall of force, but as a wall of different physics, a boundary between two versions of reality, one of which contains everything we know and one of which does not. That wave has not been detected. That wave may never form. That wave might be impossible if the vacuum turns out to be absolutely stable after all. But the fact that physics allows us to describe it, That quantum field theory contains the mathematics for it, that the measured constants of nature point toward a vacuum state where it is at least conceivable that fact says something about the universe we live in. It says that reality is not a permanent structure. It is a state, a configuration, a solution to the equations of quantum field theory that could, in principle, have been different and that might, in principle, still change. And everything we are, everything we know, everything we have ever loved or built or dreamed exists within that state, depends on that state, is made possible by that state. Not by certainty, by a balance of fields and forces and couplings and masses that happens to support complexity and life and consciousness. A balance that has held for 13.8 billion years and shows every sign of holding for incomprehensibly longer. But a balance, not a guarantee. And perhaps that is enough. Perhaps knowing that the ground is not guaranteed, that the rules aren't eternal, that existence itself is conditional, does not have to be a source of dread. Perhaps it can be a source of clarity, a reminder that the universe did not owe us its current configuration, that the stability we enjoy was not promised, that every moment in which atoms hold together and stars burn and minds think is a moment that the vacuum has permitted rather than a moment that was inevitable. The most frightening wave is the one no one would ever see coming, not because it is hidden, not because it is sneaky, but because it would not travel through reality so much as replace it. And the most remarkable thing about that wave is not that it might exist. It is that something inside this vacuum, something made of the very fields whose stability is in question, figured that out. Good night.